Every time a transformer processes a token, whether it's a comma or a scientific term or a rare proper noun, it fires up every single attention head to look at that token. Intuitively, that feels wasteful. A comma probably doesn't need the same rich attention machinery as a word carrying the main meaning of a sentence. And as context windows stretch into the hundreds of thousands of tokens, the quadratic cost of attention makes this uniform spending really painful. The paper we're looking at today, called Grouped Query Experts, or GQE, asks a pointed question. Can we bring the sparsity idea from mixture of experts, which has worked so well for the feed-forward blocks of transformers, into the attention block itself, and specifically into the query heads? To understand what they're doing, we need a quick refresher on grouped query attention, or GQA. In vanilla multi-head attention, every query head has its own key and value head. That's expensive because during auto-regressive generation, you have to cache and read all those keys and values at every step. Multi-query attention goes to the other extreme, sharing a single key value head across all queries. GQA sits in the middle. You partition query heads into groups, and each group shares one key value head. This dramatically shrinks the KV cache while keeping more expressive power than pure multi-query. But here's the catch that motivates this paper. GQA still evaluates every query head for every token. It saves memory bandwidth, but not query-side compute. Now, prior work has tried to make attention conditional in various ways. Some methods prune heads after training. Others, like mixture of attention or MoH, route across heads globally and sometimes sparsify the KV cache too. The authors of GQE make a much more constrained choice. They preserve GQA's group structure completely and only introduce sparsity within each group's query heads. Think of it like this. Imagine a restaurant kitchen where the ingredients pantry, which is the KV cache, stays fully stocked and always accessible, but the chefs, which are the query heads, only activate the specialists needed for each particular order. The pantry doesn't change. Only which chefs step up to work changes per token. Here's how it actually functions. Within each GQA group, instead of a fixed set of query heads, you have a pool of query head experts. For each token entering that group, a small router network produces scores over the experts in the group, applies a softmax to get probabilities, and then picks the top K experts. Those selected experts each compute their own attention output against the group's shared key and value. The unselected experts don't run at all for that token. The result is that only a sparse fraction of query head compute happens per token. Now comes a subtle but crucial design choice. If you just concatenate the outputs of the selected experts and feed them into the output projection, you have a problem. The router made a discrete top K decision, which isn't differentiable, so the router itself gets almost no learning signal from the main loss. The authors solved this by adding an extra slot alongside the hard concatenated expert outputs. This slot is a renormalized weighted sum of the selected expert's outputs, where the weights are the router's own softmax probabilities, renormalized so they sum to 1 across the selections. Because those router probabilities flow into this slot and then into the final output, gradients can actually propagate back and teach the router which experts to pick. It's essentially a gradient bridge between the discrete routing decision and the continuous loss. They also add one more piece, an always-on shared attention head that runs for every token regardless of routing. Think of it as a stability anchor. While the routed experts are free to specialize on different token types, the shared head provides a consistent, token-independent pathway that keeps training well-behaved. Combined with a standard load balancing auxiliary loss that prevents the router from collapsing onto the same expert every time, you get a system that trains stably from scratch. The ablation results really drive home why these design choices matter. On a fixed 30 billion token training budget at the 250 million parameter scale, the dense GQA baseline hits an average of 55.86 across HeliSwag, ArcEasy, and PIQA. A naive sparse routing scheme without the renormalized slot drops to 55.19, nearly a point below. Hard concatenation alone gets 55.43, still short. But the full GQE recipe with the renormalized weighted sum slot and the shared head reaches 56.04, actually slightly exceeding the dense baseline while activating only half of the routed query experts per token. In the main configuration of 16 query heads and 8 KV heads, that means 9 out of 16 query attention computations actually run, once you count the shared head. And crucially, on the throughput side, the prefill speedup ranges from about 1.15 times at 2K context up to roughly 1.7 to 1.8 times at long contexts of 4K and beyond, exactly where attention cost dominates. The limitations here are worth being honest about. This is a 250 million parameter model trained on 30 billion tokens, which is small by modern standards, and the accuracy match with the baseline is within a fraction of a point without multiple seeds reported. So it should be treated as parity rather than a decisive improvement. The expert pool per group is also small in these experiments, so we don't yet know whether much larger pools would unlock real specialization gains. And because the output projection is reshaped to have fewer input slots than the dense baseline, the comparison isn't perfectly parameter matched at the attention output. Still, the direction is compelling. Attention sparsity is possible without giving up quality, if you're careful about giving the router a real gradient signal. Now let's walk through some questions you might have after hearing all of this. First, why doesn't the router just learn from the hard top K selection directly? The issue is that top pick is a discrete, non-differentiable operation. When you pick the top expert, small changes to router scores usually don't change which expert gets chosen. So gradients through that decision are effectively zero almost everywhere. The renormalized weighted sum slot sidesteps this by using the router's continuous probabilities as multiplicative weights in a path that actually appears in the final output, giving the loss a smooth surface to push against when updating the router. Second, why keep the KV cache completely dense instead of also sparsifying keys and values? This is really a pragmatic choice about where the pain points are. GQA was already designed to minimize KV cache memory and bandwidth, and sparsifying keys and values across tokens would either break the cache structure or force complicated bookkeeping about which keys were computed for which tokens. By touching only the query side, GQE gets a clean compute reduction while preserving all the KV cache benefits that make GQA attractive for inference in the first place. Third, why does the shared always-on head matter so much? During early training, the routed experts are essentially random and the router hasn't figured out its job yet. So if the entire attention output depended on routing, the layer would produce very noisy signals and training could destabilize. The shared head provides a reliable baseline attention computation that every token sees, giving the rest of the network something consistent to build on while the routed experts gradually differentiate and specialize. For large-scale recommendation systems serving hundreds of millions of users, the ideas here map onto several concrete opportunities. Modern sequential recommenders increasingly use transformer backbones over long user histories, and attention compute becomes a real bottleneck when you want to model thousands of past interactions per user. GQE's approach of keeping the KV cache dense while sparsifying query-side compute is particularly attractive for ranking and retrieval pipelines because you preserve the ability to pre-compute and cache item or context representations, which is critical for low-latency serving, while cutting the per-token compute at scoring time. You could imagine routing different query experts for different types of user tokens. A browsing event versus a purchase versus a search query might legitimately benefit from different attention patterns. The other practical takeaway is the training recipe itself. The finding that naive sparse routing degrades quality unless you provide a proper gradient path to the router is directly applicable to any team experimenting with MoE-style architectures and recommendation ranking models. Teams often see MoE layers underperform their dense counterparts and blame the sparsity, when really the culprit may be router learning dynamics. The renormalized weighted sum slot combined with an always-on stabilizing pathway is a lightweight general trick that could improve MoE recommendation models even outside the attention setting.